In the last lecture, we talked about the methods for constructing multiple sequence alignments. The multiple alignment we obtain can be used as a summary of the sequences. There are several sequence profile representations that try to capture this summary. We would typically apply multiple sequence alignment to a set of protein sequences that belong to the same family. Proteins are grouped into such families based on their structure, homology, and function. Multiple sequence alignment highlights the residues that are common in all or most of the sequences. We call such residues conserved residues. Sometimes we would see a stretch of highly conserved residues, which we call a conserved region or a conserved site. If the proteins we have aligned have some common function, we can attribute that function to the set of conserved residues. In protein sequences, sometimes the residues may not be strictly identical, but may share a common physicochemical property, such as being hydrophobic. It is often useful to summarize the set of conserved residues in the form of a pattern that can act as a signature for the proteins we have aligned. When we get a new protein and want to know if it is related to this protein family, rather than performing alignments with the sequences, we can more efficiently check to see if this signature is present in the new protein. Let's now see some sequence profile representations used to summarize multiple sequence alignments. A position-specific scoring matrix is one of the most common methods for extracting a profile from a multiple sequence alignment, and it also serves as a starting point for other sequence profile representations. Given a multiple alignment, a position-specific scoring matrix can be calculated as the frequency of each type of residue within each column of the alignment. For instance, the frequency of A in that first column is 2 out of 5, which is 40%. If the length of the alignment is n columns, then the PSSM will be a 4 by n matrix. If the multiple alignment contained proteins instead of DNA, the size of the position-specific scoring matrix would be 20 rows by n columns. While the main idea for calculating the frequencies in the PSSM matrix is straightforward, we run into several problems. One such problem is that it is not clear what the best way is to handle gaps in an alignment column. For example, in this column, all of the proteins that do have a residue in that position have the letter C. Assigning the frequency of cysteine to 60% does not do justice to this strong conservation. One may easily argue that the frequency of cysteine should be 100%. For that reason, in some formulations of PSSM, the calculations are done ignoring the gaps. Another issue with PSSMs is that some amino acids have zero frequencies. Remember that we would use the PSSM as a summary profile of these proteins and use it when deciding whether a new protein should be considered related to this protein family. Saying a particular residue is never allowed to occur in a column is too strong of an assertion and falsely rejects closely related proteins that happen to have a different residue in that column. This issue happens especially when we have a small number of proteins in the alignment, such that they don't represent all the possible residues that can appear in related sequences. The sequences we have chosen to align are naturally biased because of the lack of data or lack of understanding about which proteins are related to each other and should be part of this family. An artificial solution to this problem is to add pseudo-counts to the position-specific scoring matrix, where we essentially introduce additional fake proteins just so we can raise the baseline of each amino acid frequency to a non-zero value. Mathematically, using pseudo-counts is equivalent to adding 1 to the count of each amino acid in a column and adding 20 to account for the total number of fake amino acids we have added. Some may argue that using a pseudo-count of 1 for every amino acid is not a good idea, because we are implying that the amino acids occur in equal quantities in nature. A solution to this is to make the pseudo-count weighted by the background frequencies of the amino acids. It may also be desirable to adjust the contribution of the pseudo-counts in comparison with the actual counts of amino acids observed in the alignment. This is done by introducing a parameter beta to adjust the contribution of the pseudo-counts. If we have sufficient number of sequences in the alignment, say more than 1,000, using pseudo-counts is not as necessary, so we can reduce the value of the beta parameter when we have sufficient number of sequences. Adding pseudo-counts based on the background frequencies of amino acids in nature kind of ignores the particular residue composition observed in an alignment column. One way to remedy that is to weight the frequencies by an amino acid substitution matrix, such that even if, say, a particular hydrophobic amino acid does not appear in a column, it can still have a moderate value if the column consists of other hydrophobic amino acids. One last problem I'd like to mention is that the sequences we have available are biased with the organisms that have been sequenced. The priorities for sequencing an organism may be due to scientific, medical, or industrial reasons, and such priorities do not match a comprehensive sampling of sequences available in nature. One solution to reducing the contribution of sequences from highly related organisms so that they do not dominate the results is to lower the weights of such sequences. Position-specific scoring matrices are powerful numerical summaries of multiple alignments, but they are neither pleasant-looking nor easy to interpret. Sequence logos provide a nice visual representation of the position-specific scoring matrix. Each position in a sequence logo is calculated from a column of the multiple sequence alignment. Let's now see how the sequence logo is calculated. I'll first explain some terms from information theory. The entropy in a column represents the amount of uncertainty in that column, which is in a way opposite of how conserved that column is. The entropy is calculated for each column as the negative sum of the frequencies of each amino acid in that column multiplied by the log 2 of the frequency of that amino acid. Since we use the logarithm of base 2, the units are in bits. The maximum entropy would happen when we have equal numbers of each of the 20 amino acids, which represents the least amount of conservation. The entropy value of such a column would be log 2 of 20, which is roughly equal to 4.3 bits. And this is of course for a protein alignment. The maximum entropy of a column from the multiple alignment of DNA sequences would be log 2 of 4, which is equal to 2 bits. The smallest entropy would happen if a column consists of only one type of amino acid, in which case the entropy would be 0. The level of information in a column, which can be taken as the level of conservation, is calculated as the maximum possible entropy minus the entropy of that column. The level of information dictates how high the letters in the sequence logo will reach. The height of each residue is then calculated as the frequency of that residue multiplied by the information level of that column. For protein sequences, the maximum height is 4.3 bits. So if a column in the multiple alignment consists of only one type of amino acid, it will show up as a letter that is 4.3 bits high. Let's work out an example sequence logo. I'll calculate the letters of the logo only for the first column of this alignment. In the first column, we have 40% A, 40% L, and 20% I. the entropy of that column is calculated as the negative sum of each amino acid frequency in that column multiplied by the log 2 of that frequency. We find the entropy of the first column to be 1.52 bits. The information level of the first column is log 2 of 20 minus 1.52, which is 2.8. So all the letters in the first column of the logo, when they are stacked on top of each other, will reach 2.8 bits. We can now calculate the height of the individual letters. The height of A is the frequency of A in that column multiplied by the information level of that column, and we get 1.12 bits. Similarly, we get 1.12 bits for L and 0.56 bits for I. The letters are then stacked on top of each other, ordered by their heights. The tallest residue would be on top. While sequence logos provide a nice visual representation, they cannot easily be used as a signature such that a new protein can be judged to belong to the same protein family. Prosite patterns are text-based summaries of protein profiles. The name Prosite, which stands for protein site, is the name of a search tool and online database that contains a large collection of such patterns extracted from multiple alignments of protein families. If you were to search for such a pattern in a programming language, you would typically use what is known as regular expressions. So I will show you the regular expression counterpart of each of the notations used in Prosite. A letter X is used to represent any amino acid. In regular expressions, a period is used for the same purpose. Letters enclosed within square brackets are used to provide options. For example, here we can have an A, L, or T in that position. This notation is the same in regular expressions. In Prosite, curly brackets means we can have any letter other than the ones listed. In regular expressions, this is accomplished by placing a caret symbol inside the square brackets. The caret symbol is used to negate the list of characters. In Prosite, a number within parentheses represents repetition. Here, this is meant to say we have A repeated 3 times. In regular expressions, this is written as A curly bracket 3. 2 numbers inside parentheses separated by a comma represents a lower bound and upper bound of repetitions. Here 2, 4 represents 2 A's, 3 A's, or 4 A's. A less than sign marks the beginning or the end terminus of a sequence. In regular expressions, we use a caret symbol for that purpose. A greater than sign marks the end of the sequence. In regex, we use a dollar sign for that purpose. And that's pretty much all the rules used in Prosite patterns. Let's now re-examine these example patterns. In the first example, the Prosite pattern will represent an alanine or a cysteine followed by any amino acid, followed by a valine, followed by any 4 amino acids, and followed by any amino acid except glutamate or aspartate. The second example represents a pattern that appears at the beginning of a protein sequence where we have an alanine followed by any amino acid, followed by 2 of serine or threonine, followed by 0 or 1 of any amino acid, and followed by a valine. Sequence profile representations that we discussed so far tend to oversimplify the multiple alignments, especially when it comes to deciding whether a new sequence contains the same profile. They do not perform as well as some of the more advanced statistical methods. One of the most powerful statistical representations of multiple alignments is hidden Markov models. A hidden Markov model is a state machine composed of nodes and transitions. Here you see 3 types of nodes: the match nodes, delete nodes, and insertion nodes. The primary advantage of hidden Markov models over position-specific scoring matrices is that gaps are now position-dependent. Each node of HMM has transition probabilities that tell us the likelihood of following a particular transition out of that node. For example, this M1 node may have transition probabilities 0.1, 0.6, and 0.3. When we are in M1, we will go to M2 with the highest probability, but there is still a chance that we may go to D2 or I1. The match nodes are responsible for generating the amino acids. For each match node, we would have a table of emission probabilities for each of the 20 amino acids. For example, when we are in M1, we produce proline with 90% probability. The rest of the 10% of the time, we produce one of the other amino acids. When we are in M3, we produce a threonine about 70% probability or a serine with about 20% probability. The insertion states can also similarly have emission distributions associated with them if we want to represent which amino acids are being inserted. Any particular path through these nodes, transitions, and emissions represents the production of a corresponding amino acid sequence. Let's, for example, walk through the path highlighted here and assume the transition probabilities are as shown. And let's also assume that we produce a proline amino acid when we are in M1 and an asparagine amino acid when we are in M4. The probability of following this path and producing proline asparagine as a sequence is obtained by multiplying the transition and emission probabilities. Given a hidden Markov model, we can ask and answer several questions, such as, what is the most likely path? The answer to that question would give us the most representative sequence for the HMM. What is the probability of a sequence being produced by an HMM? I'd like to point out that the same sequence can be produced from multiple paths, so we would need to add up the probabilities of all the paths that produce the sequence. And finally, how can we actually construct the HMM and identify the transition and emission probabilities from a multiple sequence alignment? It should not surprise you to learn that these questions can be answered using dynamic programming. We can use dynamic programming because the probability of a node can be decomposed into probabilities of transitioning into it from one of the previous nodes. For example, let's calculate the probability of the most likely path that takes us into M3. We can get to M3 from one of the three options, D2, M2, or I2. The score of each of these options can be calculated as the score of being in that previous state multiplied by the transition probability of getting into M3 from there. We would then select the highest of these scores and make a note of which direction resulted in the highest score. Just like when we applied dynamic programming to sequence alignment problem, we would begin from the start state and calculate the score of each state from the scores of the previous states until we get to the end state. By that time, we would know the best direction leading into each state. We can then backtrack from the end state using these best directions to find out the most likely path we would follow from start to end. If you want to find the most likely path of states that can generate a given protein sequence, you would also need to consider the emission probabilities, which I did not show here. The other questions we had for HMM can be answered using similar decomposition strategies. For example, when you want to find the probability that a sequence would be produced from the HMM, you would consider the sum of all options that can produce the sequence rather than the maximum valued option. I'm not going to go into details of these algorithms here. Given a model created from a protein family, hidden Markov model is very successful in evaluating whether a new protein belongs to the same family. Sometimes we may also wish to know how similar two protein families are, which involves comparison and alignment of two HMMs. This is not much different in nature than sequence alignment. A similar comparison can also be done with position-specific scoring matrices. A simple correlation measure between PSSM frequencies in each column can help identify the positions in the protein family profiles that are highly similar. In summary, sequence profiles can be extracted from multiple sequence alignments and provide a signature for the protein families. Sequence profiles can be used to evaluate whether a new sequence belongs to the same family or has the same pattern of conserved residues. Sequence logos and Prosite patterns are easy to interpret and present, which is good for human consumption, but may not be accurate enough for some applications. Hidden Markov models are a position-dependent, probabilistic representation of protein profiles that are successful in evaluating family membership of proteins.